Okay, this is exam 3, 102, spring 2016. Here I have a 3 coulomb charge, that's Q, traveling at 10 meters per second, that's V, and a magnetic field, that's B. It's orthogonal, that means it's moving at an angle of 90 degrees. So I say F is equal to QVB sine theta. That's going to be 3 coulombs, 10 meters per second, 4 Tesla times the sine of 90. Of course, the sine of 90 is equal to 1, so I'll just leave that out. So that's 30 times 4, 120 newtons. So B is the right answer. Which of these statements about the magnetic force is true? The magnetic force is centripetal. That's true. Magnetic force is always perpendicular to the velocity. That's also true. And it always causes circular motion because it's a centripetal force. That's what it does. So E is the right answer. At some moment, an electron moves with a velocity of 1 meter per second, that's V, in the same direction as, that means that theta between the vector V and the vector B, that angle theta is 0 degrees. And so we could probably just stop right there and say that the answer is A. And the force is acting on the electron. Well, if we want to go on and do the whole thing, which some of you might have done, I would say the charge on an electron is 1.6 times 10 to the minus 19 coulombs. V is 1 meter per second. B is 1 Tesla. Times the sine of 0 degrees. Sine of 0 is equal to 0, so this whole thing is equal to 0. But some of you might have put D because you didn't get that angle right. An electron moves through a region of crossed electric and magnetic fields. The electric field, 2,000 volts per meter, is directed straight down. The magnetic field is directed to the left. For what velocity of the electron will the electric force exactly cancel the magnetic force? Okay, so we're just really looking for the magnitudes here. So the first thing we want to do is find the electric field, the force due to the electric field, the electric force, and it's going to be Q times E. So that's going to be 1.6 times 10 to the minus 19 times the electric field, which is 2,000. So it's going to be 3.2 times what, 10 to the minus 16? Yeah, 10 to the minus 16. That's in volts per meter. I'll write it in newtons. Or actually, that's just going to be in newtons. So that's my force. And now I want my magnetic force to also equal that. So my magnetic force is 3.2 times 10 to the minus 16 equals QVB sine theta. Q is 1.6 times 10 to the minus 19. V is what I'm looking for. B is 0.8 Tesla. And I solved that for V. They're orthogonal to one another, so I will, the velocity and the magnetic field. So I will take theta to equal to 90, and now I solve this for V, which is going to be 2,000 over 0.8. Notice if you kept your variables here and didn't solve it and just substituted in down here that it would be a little bit easier. But so that's, I get 2,500 meters per second. So for number 4, A is the right answer. Let me pause this for just a second. Okay, well, I didn't ask this question, but I could have. What direction is the electron traveling? In order for this to exactly cancel out the magnetic force, in order for the electric force to exactly cancel out the magnetic force, what direction must the electron be traveling? Well, I know that it can neither be in the x nor the y direction. Well, excuse me, let's step back. So I know that the electric force is going to be up, rather. The electric force is up because it's an electron and the electric force is opposite the direction of the electric field. So the electric force, regardless of the velocity vector, is going to be up. So I want to find a velocity vector that will give me my magnetic force to be down. So I can use my right-hand rule. And now I know that since B is in the x direction, F is in the y direction, that the direction of the velocity vector has to be in the z direction because it's orthogonal to both F and B. So I use my right-hand rule. My thumb is going to go in the direction of FB, and my fingers will go in the direction of V, and my palm will point in the direction of the magnetic field. So that tells me that, let's see, what is that? So thumb, that's a little tricky. That tells me that the velocity vector has to be coming out of the page in order to provide a force like this. Isn't that right? Yeah, out of the page, but it is a negative particle, so the velocity vector is opposite that, or into the page. And again, I didn't answer that question. I didn't ask that question, but I could have, so for future reference. Consider a long, straight, thin wire carrying a steady 0.5 amp current. The value of magnetic field, 0.5 centimeters, is what? Well, my current is 0.5 amps. I'm looking at a distance equal to 5 centimeters, which is 0.05 meters. Let's go look at my equation sheet. Honestly, I forget these things. So I'm looking for my magnetic field from a long straight wire. That's this B equal mu naught I over 2 pi r. So B is equal to mu naught I over 2 pi times r. My mu naught, if you forget, you can look over here. Mu naught is 4 pi times 10 to the minus 7. So that's 4 pi times I, which is 0.5 amps, divided by 2 pi times r, which is 0.05. All right, so my 2 pi cancels and leaves me with that. This cancels and leaves me with 1. So I'm looking at 10 to the minus 7 over 0.05. And I get 2 times 10 to the minus 6 Tesla, or 2 microtesla. A is the right answer. Which of these statements are true? Opposites of a magnet attract. Opposite poles of a magnet attract. Uh, okay, that's true. Magnetic monopoles do not exist. That is also true. All permanent magnets are ferromagnetic. That is a true statement. Now, it's not true that all ferromagnetic materials are permanent magnets, but it is true that all permanent magnets are ferromagnetic, that they're able to be magnetized. So D is the right answer for number 6. The Earth's magnetic field plays a role in which of these phenomena? Atmospheric refraction, no. Mirages, no. Aurora borealis, yes. High energy particle showers, no. Now, those high energy particle showers are related to the aurora borealis. They're caused by that, but magnetic fields don't play a role in the actual particle showers. They just interact with the showers to direct those high energy particles into the atmosphere at high latitudes. The current goes to the solenoid. What is the direction of the magnetic field inside of the solenoid? Well, it's either to the left or the right, so we can get rid of these, and these, because that's just the way that solenoid works. Let our finger go in the direction of the current, so imagine our thumb pointing up of our right hand, and so our fingers are going to go to the left. So my magnetic field goes in this direction. Positive particle approaches a current carrying wire shown here. What is the direction of the current that causes the particle to travel in the path that's shown? All right, so I have a force in this direction and a velocity vector in this direction. So first I want to ask myself the question is, what is the direction of the magnetic field? Well, velocity is down, force. The magnetic field is into the page. So I have a magnetic field that's into the page over here and out of the page over here. So what is the direction of the current? Well, use that third application of the right-hand rule. If my thumb is pointing to the left, my fingers go in on this side and out on this side. So it must be A is 9. Current travels through the wire shown. What is the direction of the force on the wire? Well, this is a lot like that first application. Fingers in the direction of I, they fold towards B, and I get my thumb into the page. So E for number 10 is right. When is the initial direction of the positively charged particle? When it is just magnetic field. All right, this is a positive particle. Remember that. It's V is to the right, magnetic field is down, so this thing is going to move into the page. The force that it feels will be into the page, it'll go away from you. So number 11 is C. Organize these in order of highest to lowest frequency. All right, remember, high frequency is a high energy, so I'm looking at high energy things, so I can get rid of this. It looks like A is right. This comes first in high energy or high frequency. That's next, and that's next. Let's just check these others. No, this is all out of order, the ultraviolet, radio, infrared, so that's not right. Radio is the lowest energy that you can have, so it shouldn't start with the lowest energy. And here, this is out of order too. If I was going from low to high, I would switch these two, but it's not right. So A is right for number 12. Which of the following statements is true? Okay, Newton believed light was a wave because of refraction. That's not true. Huygens actually believed that. Einstein showed light was a particle because of interference. That's not true. Einstein showed light was a particle because of the photoelectric effect. Huygens believed light was a wave because of refraction. That's true. And Young showed light was a wave through the double slit experiment. That is also true. So 3 and 4. D is right. D is right for number 13. These two mirrors at an angle of 100 degrees to one another. A ray of light is incident at 40 degrees on the first mirror. What is the angle of reflection with respect to that perpendicular line? Well, let's see. So if this is 40, that means this angle is 40, and that means this angle is 50. If that angle is 50, that means this has to be 30 degrees, and if that's 30, that means this is 60. So the right answer is A, because my reflected angle will be 60 degrees over here by the law of reflection. So number 14 is A. A ray of light strikes a thick sheet of some transparent material at an angle of 30 degrees with the normal. Find the angle of a refracted ray within the glass. So I have this in air, it comes along. This is 30 degrees. I have n equal 1 over here, n equal 3. It's going to bend, because it's going to a higher index, it'll bend towards the normal, so my angle will be smaller. I can get rid of that. In fact, it should bend a lot because this index of refraction is so small. So I'm guessing that my answer is going to be B now, just because if I look at this index of refraction, it's so big, it must be a really big bending of this ray. But let's just check that. So I have 1 sine of 30 equals 3 sine of theta. So I have 0.5 over 3, and then I'm going to do the inverse sine of that. And I get 99.5 degrees. Or just round that up to 10 degrees. So B is indeed the right answer for number 15. Light travels through 3 media as shown here. And which medium is the light traveling fastest? Well, let's see. Here, it bends from here. It goes in this direction. So that means that it's traveling faster in medium 2. And then it comes over here and it's going to slow down here and cause it to bend in that direction. So it's traveling faster in medium 2 than it is in medium 1, and it's also traveling faster in medium 2 than it is in medium 3. So I can find from here that V2 is bigger than V1, and then also from here I find that V2 is bigger than V3. So V2 is the bigger speed, B. If the material has an index of refraction of 1.33, the speed of light through it is what? Well, n is equal to, or V is equal to C divided by N. So that's 3 times 10 to the 8th over 1.33. Should be a little more than 2. So I can look at this and tell you right off that A should be the right answer, but let's just double check that. 3e to the 8th, 0.33. It's 2.26 times 10 to the 8th. So that is right. Meters per second. Ray of light travels from water to air. What is the appropriate angle of incidence where total internal reflection will occur? Okay, well, in total internal reflection, this refracted angle will equal to 90 degrees. So this is just law of refraction. I say 1.3, that's the index in water, times the sine of theta, this is going to be my critical angle, is equal to 1, that's the index in air, sine of 90. So theta c is the inverse sine of 1 over 1.3. I get 50 degrees. A, number 18. This is a figure of a fiber optics cable. A light ray coming from the acceptance zone will experience total internal reflection within the core. What must be true about the indices of refraction? Remember, in order for us to get total internal reflection, I have to have it moving away from the normal. So that means it has to be traveling faster when it enters that second medium. So that means that the index of refraction for that second medium has to be smaller. So n of the cladding has to be smaller than n of the core. In fact, usually what they have is they just have, the core with nothing around it. It's just sitting in air. In fact, that's not entirely true because they often do have a covering over it, but the index of refraction has to be less than, for the cladding, has to be less than the index for the core. So number 19 is C. Atmospheric refraction did not occur. How would the apparent time of sunset be changed? Well, let's just remember what this atmospheric refraction does is that if you're standing over here and the sun is over here, you shouldn't be able to see it, but because of refraction, those light rays you see it even after you shouldn't have seen it. So without the atmosphere, and without that phenomena of atmospheric refraction, you would have an earlier sunset, but you wouldn't see the sunset later than it actually is. Mirages, even though they look like reflection, they are actually a result of refraction. Image is found to have a negative image distance. Which best describes this image? Well, if it has a negative Q value, that means that it's a virtual image. It could be any one of these things. It could be inverted. It could be smaller than the object, or it could be imaginary. Actually, hold on just a second. Okay, I might come back and change this a little bit because this is a little bit confusing because we haven't really gotten to lenses yet. I just want to make it very clear. Now, if it has a negative image distance, that means it's a virtual image. That's also, at least for mirrors, is going to mean that it's smaller than the object. And it is upright. So it could either be, if you're thinking about mirrors only, it could also mean that it's smaller than the object. So I'm going to rewrite this question. I'll still keep it at 22, so the key will still be the same, but this question will be slightly rewritten. And I'll try to get back and put a note in it on the YouTube video. You stand 2 feet away from the plane mirror. How far is it from you to your image? All right, you're 2 feet. Your image is also 2 feet. So that means that the distance from you to your image is 4 feet. So A is the right answer. Mirror produces an upright image. The object is 8 centimeters high. HO is 8. And to the left of the mirror, the image is 16 centimeters high. Where is the image located? All right, so let's see. I have a bigger image. So HI is equal to 16 centimeters. That tells me that this has to be a concave mirror right away because the image is bigger. It also tells me that it has to be an upright image. So my magnification is going to be positive. All right, so that means that my magnification is going to be positive because it's upright. Now, the center of curvature here is 8 centimeters. So that means that my focal point is equal to 4 centimeters. And this is a concave mirror, so it has a positive focal point, as unlike the convex mirror. And what else do I know? I want to know what is Q equal to. All right, so let's write down some things that I know. I know that the magnification is equal to HI over HO. That's plus 16 over 8. That's equal to 2. I also know that M is equal to negative Q over P, which is equal to 2. And then I also know that 1 over F, which is 1 over 4, is equal to 1 over Q plus 1 over P. I'm going to have to do some substitution here because I'm looking now for Q. And so I solve this for P. I say P is equal to negative Q over 2. And I'm going to plug this in down here. So I get 1 over 4, or rather not there, I'll plug it in here, equals 1 over q plus 1 over negative q over 2, which is going to be negative 2 over q, negative q over 2. And then that's going to be 1 over 4 equals negative 1 over q. So q is going to equal to negative 4. Notice that the object is to the left of the mirror. Since this comes out negative, it is a virtual image. So it's going to be to the right of the mirror. So A is the right answer. 4 centimeters to the right of the mirror. Number is that 24 is A. Okay, tough question. You have lots of things that you have to think about there. You have to figure out what kind of mirror it is, what kind of magnification it is, what are the signs of all the various things, the magnification, the image distance, the object distance, all that jazz. So not an easy problem. Lots of things to think about. All right, almost done. A concave mirror can produce which of these? Concave mirror can produce a virtual image. It can produce a real image. It can produce a magnified image, and it can produce an upright image. So all of these is true. And a concave mirror has a focal length of 10 centimeters. Object is 10 centimeters from the mirror. What is the image located? So concave mirror has a focal length equal to positive 10 centimeters. The focal length is positive for a concave mirror. P is 10, so I have 1 over F equals 1 over Q plus 1 over P. That's 1 over 10 equals 1 over Q plus 1 over 10. Q is equal to 1 over 0, but that is undefined, and so there is no image. There's no image when your object is at your focal point. So C is the right answer. And then which of these rays is or are drawn incorrectly? Well, let's see. Ray number 1, which is right here, it looks like this. It comes along in this direction, and then it reflects back on itself. So ray number 1 is correct, through the center of curvature and back on itself. Ray number 2, through the focal point and back on itself. Ray number 2 is correct. Ray number 3, parallel to the axis and through the center of curvature. Okay, that's not right. It should instead go through here and through here. And so my image should be right here. So ray number 3 is not correct. C for number 27. All right, there's the answers. Remember, 22 might be changing, and I will let y'all know how it changes.